All right, on to the second lesson in this unit. We're looking at gravitational potential energy. Gravitational potential energy, and we shorten this up to GPE because we don't like writing that out all the time. All right, so gravitational potential energy. I can explain, calculate, and compare gravitational potential energy and kinetic energy. And we're going to talk about kinetic energy later in this lesson because they really go hand in hand. And it's just easier, I find, to teach them together as we go through. So gravitational potential energy, or GPE, is the common form of energy. This is the energy that results from an object's vertical position. So if you are suspended above the surface, you have what we call stored energy. So how do we calculate this particular energy? Well, we need to take Newton's second law, which is the FU law, and from that, it's really force due to gravity if we're talking about an object that's above the surface. Taking that formula, we head into our work or mechanical energy formula of force multiplied by displacement. And since we're talking about a vertical displacement, we're talking about an object above the surface. The force acting on that object is Fg. So that means that the force in our work formula is replaced with force due to gravity, delta D. Force due to gravity is mass times our G value, delta D. And to match up with the textbook and common practice is to switch it to this form here. So it becomes gravitational potential energy. So EG is the notation. So it's just work. It's all the same. EG equals mg, and then they go h. And h is the height above the reference point. I'll talk about that a little bit later on. So h is the height above the reference point. Now, for the most part, our reference point will be the surface of the Earth. But you can really measure anything, measure your energy relative to any point. All right, so you can move that line around a little bit. So that being said, a couple of quick examples, and everyone gets excited when they get into this one because the algebra, the math becomes a lot easier. So find the gravitational potential energy of a 20 kilogram hanging pot located 5 meters above the ground. Once you see GPE, you just need to go to your formula sheet and get EG, and it's mgh, mass times gravity times height. So the mass is 20, gravity is 9.81, and the height is 5. So there we are. There's really no catches with the algebra in this unit. So if you were waiting for one, hate to disappoint you, but nothing's coming. That ends up being 981 joules. So therefore, that flower pot, and it's potential energy, so it's stored. So therefore, I'll write the therefore statement a little bit different. The stored energy is 981 joules. And the only reason I'm going to write it that way is because I just want to get that into your, sort of enter that into your mind, like gravitational potential energy. It's really stored energy. All right. If a 5 kilogram ball falls from 15 meters to 5 meters, how much GPE was lost? So here we got a frame of reference question. And I told you that the surface of the Earth is a reference point that we can use all the time. And if we want to do that, I'm going to show you two different ways to calculate this. So the first one, if we calculate the gravitational potential energy at 15 meters, so the mass is 5 times 9.81 times 15. We would get how much energy is located, or how much energy it had at that height. 9.81 times the 15. So we have 735.8 joules. Then, if we calculate how much energy it had at 5 meters, oops, center it a little bit better for us. So mgh, and I'll call that height 2, 5, 9.81 times 5. We get 245.3 joules. So we're looking at the change in energy, how much energy was lost. So delta Eg would equal Eg1 minus Eg2. That would equal 735.8 minus 245.3. And when you do that, 35.8, we get 490.6 joules. So therefore, it lost 490.6 joules of energy. So now the question, and some of you will be asking, is there a shortcut? Because I got method number 1 up there. The answer is absolutely. If we're talking about an elevation change, I'm going to take the formula from here, that delta energy change, and I'm going to talk about it up here. So if we're talking about an energy change, gravitational energy change, between height 1 and height 2, let's expand this out and take a look. We have mgh1 minus mgh2. Now I know everyone here is just absolutely top of their game with the algebra skills, and you'll see that they both have a common factor. Both of them have an mg in them. So that means we can common factor out mg. So we get mass times gravity, and what's left? We have height 1 minus height 2. What is height 1 minus height 2? How can I rewrite that? Well, that's just delta H, the change in height. So the change in gravitational potential energy, we can write it this way. And that would mean that if you're going to answer this question, the second method, you'd be starting with what I have in the box. So change in energy, gravitational potential is equal to mass g delta H. The mass, again, was 5. Gravity was 9.81. And delta H, for this example, I'll do 15 take away 5 for argument's sake. But we end up with 5 times the 10 times 9.81. We get 490.5. Surprise, surprise. So therefore, same as the previous therefore statement. So really method 2 is more efficient, far more efficient, but we really needed method 1 to get there. Okay, so you're more than welcome to use method 2 when you're dealing with change in gravitational potential energy. So next, I guess I got to pause it because I got to draw a roller coaster. So, et voila, a roller coaster diagram has appeared. So the roller coaster is shown. I want to answer the following. What's the gravitational potential, excuse me, at point A? Well, this is a question that's poorly done on the test. And you know what? I'll give you a hint. This is a test question. And it's always poorly done. And I'll explain the why. And it's because students are so hung up with numbers, you got to kind of let the number thing go, just for a little bit. Gravitational potential energy equals mgh. All right, we already know that. It's no trick here. The trick comes in is that the mass is unknown, and that really freaks out people. You do not need to know the mass. People calculate roller coaster, they do the roller coaster calculations without a mass because it depends on how many people are in the car or how many people are in the roller coaster, how heavy the people are on the roller coaster. So we just leave the mass as m. Okay, I know that's freaking a lot of people out, but you can have variables in the answer. It's okay. The height is 30 meters. So when we do the calculation, what's the potential energy at point A? It's just the 9.81 times 30, and you get 294.3 joules, 294.3 m joules of energy. The mass is a variable. It doesn't matter. Okay? Because the mass of a roller coaster is going to change depending on its composition. So therefore, it would have, and I know it's bothering a lot of people even now, but it's okay. And that's why people don't do poorly on the test, because they won't do this question. They refuse to just put an M in there. They say there's no number, I'm not doing it. What's the change in GPE from point A to point B? Well, EG would equal now we're doing delta, mg delta h. So I'm using the formula from part 2 of the previous question. M's unknown, I know, it's okay. You'll survive. 9.81 delta H, 30 take away 12. And we go ahead and do that calculation, and we find that the energy, the lost energy, is 176.6 m joules. So therefore, change in energy is 176.6 m joules from A to B. C. What is the gravitational potential energy at point B? Well, Eg equals mgh, so m 9.81 multiplied by 12, and we get 117.7 m joules. All right. Now the bonus question I want to throw on here, I'm going to add it in. When is Eg equal to 0 joules? When is gravitational potential energy equal to 0? And the answer to that is at point C. The height is equal to 0. If you have no height above the ground, you have no potential energy based on our reference system. So that leads to an interesting question as to what happened to that energy. We'll talk about that in a future lesson. All right, so the second part of this one, like I said, I do potential and kinetic energy together, so that's just Ke. So kinetic energy is the energy contained in a moving object. We can derive the equation for kinetic energy using our equation for work. All right, so work equals force multiplied by displacement, and our kinematics equations. So what are the equations we're going to use? Well, first thing I want to do, I'm going to replace both force and displacement using one of their equivalent formulas. So the easiest one for force, we only have the one, and that's mass times acceleration. So when I go to find my kinetic energy formula, Ek, I'm going to replace F with mass times acceleration. Now, what am I going to replace delta D with? Well, I need to pick a formula that has acceleration and delta D in it, and V2 and V1. So the easiest kinematics one is V2 squared equals V1 squared plus 2A delta D. So that's just from our kinematics formulas. First thing we're going to do here with kinematic energy is we're going to assume that V1 is equal to 0. And the explanation for that is pretty much we want to find the maximum velocity. We're looking for the uppermost velocity. So to keep the explanation very simple without going into a whole lot of detail, is we're interested at that maximum velocity, what the kinetic energy is. Okay, so that would mean, therefore, our formula is now reduced down to, since there's only one velocity, I don't need the subscript anymore, is that V squared equals 2A delta D. All right, so substituting or solving for delta D, it would just be V squared over 2A. That's my delta D. So there is my replacement here. Just replace that with green, so I'll just show the arrows coming over. So inside, we now have V squared over 2A. When you do the simplification, acceleration drops out of here. And we end up with mv squared over 2. Or the more common way the formula is written is 1/2 mv squared. All right. So there is your formula for kinetic energy. So I'm going to finish up the video with some examples, or the next video with some examples on kinetic energy and how that works. And then you can head off and try the homework.